this recording can be seen correctly. Remember, this was 400 nanometers, this was 700 nanometers, and then we converted those into energy, right? We converted those into energy. Then we could add the energy. The energy of A would equal the energy of B plus the energy of C. And then from that energy, now we could get a wavelength. Okay, that was part A. And then, just to make that clear, what that means, you take a look at the rubric. We calculated the energy of B, energy of C. We added those two energies together, and then we were able to use the same equations that we used to find the energies from those wavelengths to go backwards and get the wavelengths from that energy. All right. Yeah, then we get our answer there. Okay, so that's good. Now for part B, calculate the maximum kinetic energy of the electron ejected by the metal. So we're just using the photoelectric effect here, and then this is the kinetic energy that's going to be for the thing that's ejected, and then we're just taking the amount of energy minus the work function, and they gave us that work function. So yeah, they give us a work function here, and then we're using the energy that we calculated for B, right? And we're saying that that photon, if it drops this far, if the electron drops that far and hits a photon, it's going to release an amount of energy that was concomitant to this wavelength. So we calculated that. So then we take that energy, subtract this work function, and that'll be the kinetic energy of the ejected electron. See, that's right here. Everybody cool with that so far? Okay. I mean, can you see like the math here is not that hard? It's just subtraction, addition, division. There's nothing really weird. There's no big algebra, nothing. The hard part is, can you identify what the components of these things are? Remember, if you feel the need to do something tonight that's helpful, well, this is only helpful if you've been studying. If you've been studying, then go through the formula sheets. And on each equation, say, what's this, what's this, what's this, what's this, what's this, what's this. Okay, and if you can identify all those things, that'll be the best sort of last minute review that you could do. Just reading definitions and stuff isn't going to help. Calculate the de Broglie wavelength of the ejected electron. So we just calculated the energy of the electron. And then what they said in an admittedly sort of strange thing, I'm wondering why. So they want the momentum. Oh, I see. Okay. Because the de Broglie wavelength equation is lambda is Planck's constant over momentum, they use the kinetic energy to calculate the momentum. Now, granted, what you could have done is you could have said this is 1/2 mv squared, right? And we know the mass of an electron, so you could have found the velocity of the ejected electron and then just put in mass times velocity if you wanted, you know, so that you could just use this equation straight. Use Planck's constant divided by that. So they just wanted to do lambda is going to be h over mv. That's what they wanted to do. So how do you do that? And they did it by manipulating kinetic energy. Yeah.
You said when you just solved for momentum like that, you got a different answer.
No, I did like some sort of algebraic thing thinking it would work, and for some reason it didn't. Because what I did is, I think the momentum that I used was what? Well, okay, E is PC, right? Okay. Do you see the problem here? Because that means P is going to be E over C. This P, yeah, for a certain, this P is not the same as that P for some reason. Because this is like solving for that. It's like getting it for MV. So it's like extrapolating the velocity from this. I'm not sure why it comes out to be different, to be honest with you. E is the amount of energy. Oh, yeah, that's why it's different. Well, mathematically, it's going to be different because this says it's this energy. Ah, okay, that's why. what is this energy? So now I understand. Okay, now I understand. There's two ways, like the way that they did this here is basically they said P is mv, right? So use this kinetic energy to find that V, plug it in, you'll get the right answer. Or what they did is use algebra to sort of tweak kinetic energy equation and get P, whatever, okay? What I was thinking is, well, can I use the equation that says E is, what is it, PC? P times C? Yeah, E is PC. So can I just stick this into there? What is this? What does that say? Yeah, maximum kinetic of what? Yeah, this is the kinetic energy of the electron. What is that? What does that energy mean in this equation? Or even in this equation? Yeah, it's the energy of a photon. That's why it didn't work yesterday. Do you see that? So I took the wrong energy. I put the kinetic energy into the energy of a photon. That's why it didn't work. Okay, so there you go. Yeah, so that's why we have to do this. And again, the easiest way you could have done this, if you know this is kinetic energy, and you know the mass of an electron, you could solve for V, right? Then once you solve for V, multiply it by m, and you get this. So you could have just taken that and stuck it in there. And then you'll get the right answer. All right? So I'm not sure why that wasn't clear yesterday, but it's glaringly obvious. All right, so then we shall move on. Then photons emitted during which of the transitions when incident to metal surface will also result in electrons being ejected from the metal. All right. We know from the photoelectric effect equation that Ke, right, of the electron is going to equal to this sort of HF, or energy, of the photon minus phi. All right, so there's the A, B, no, okay, so they just do A, yeah, A and C, that's it. Okay. How much energy is involved in these photons? Okay, we already calculated it, right? Remember we calculated the energy for A? The energy of A, it's when we were trying to do part A. EA was the energy of B plus the energy of C. Remember this? And then I took EA and got a lambda from it, yes? So the energy of A, we know the energy of A, and we know the energy of C. Have I lost anybody yet? Okay, so because I'm sure nobody wrote this down, let's take a look at the energies of A and C. The energy of C was 1.8 electron volts. And remember, we did that just by using the energy statement, the energy of light. And then the energy of A is 4.9 electron volts. Okay, so let's go back to our problem. And we will say EA is 4.9 electron volts. And EC is 1.8 electron volts. So, from that, which of those is going to cause that metal to release an electron? Vivian. The second one, EC, and why? Because you're guessing, right? Okay, what is the photoelectric effect equation? Give your phone. So find it for us. We'll wait. I'm counting on you to get 5.
No pressure.
Sure, just joking around.
No pressure. Just
No pressure. It's either you or us. Scratching. Who else? Who else can pull a 5? Aaron? Sorry, okay, did you find it? I'm just jabbering. E is HF? No, that is not the photoelectric effect equation. That is the energy in light. So that's the energy in the frequency of light. There's only like 4 equations. You are down to 3.
actually, it's 5. It's just that one's
No, it's not lambda because lambda is the de Broglie wavelength equation. So now you are 50-50. Which one? And no, that is the amount of energy in a certain mass. So you have helped us to narrow it down to. Go ahead, say it. Yes. And see, that is a very good exercise, right? And it is important for you to do that. I said it at the beginning, I said it before, and I'll say it again. Go through the formula sheet tonight and make sure that you can identify everything and have a picture of what it means and what you use it for. Especially with these nuclear problems, right? The first question, E is HF. That is the energy in what?
Light.
In light, right? The second one, KV max equals HF minus phi. That is what? Photoelectric effect. That should be light hitting a piece of metal and ejecting an electron. Most commonly used in light hits a piece of something and creates electricity. Solar cells, most commonly used in solar cells, right? Okay, then we have lambda is what over P? H over P. So that's what? Yeah, the Broglie wavelength, which is the wavelength of matter, right? Any piece of matter that's moving has a wavelength. And then the last equation, obviously everybody's familiar with the last one, equals mc squared. Just look at it and you'll know what it's for. E is energy, M is, and C is speed of light. So it's just telling you the amount of energy in any amount of mass is that mass times the speed of light squared. Okay, so let's try this. Vivian, which one of these is bigger, EA or EC? EA. Now, when we do that equation which you gave us, KE equals HF minus phi, all right? Alvin, what does phi mean? Okay, I don't know what that means. Explain.
How much energy you need to take out an electron.
Haha. What is this question asking? Photons emitted during these transitions when incident on a metal surface. Blah, 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 blah. Electrons ejected from metal. So in order to eject an electron from metal, what must you overcome? Yeah, you must overcome the work function. Which of those is bigger than the work function? This is why, like, your solar cell doesn't work in the dark. Because that frequency of light doesn't have enough energy to stimulate it to go. Okay? If you could create something that could be a broadband, broad spectrum absorber and converter of electromagnetic or energy to electricity, then you would become bigger than Bill Gates, Steve Jobs, whatever. Because if you could patent that, actually, some people would say that you would get murdered. Probably. I don't know, all the conspiracy theorists who think that like big oil owns everything. All you have to do is just make sure you patent it first, and then once you've patented it, spread it out on the blogs, you know, like all the tech blog things, and then you'll be good. Because they can't murder you once you've already invented it.
Then you go hide on a private island.
What's that?
Then you go hide on a private island.
That you own, like Australia. I think I'm going to buy Australia. I'm gonna kick out all these weird people. It's gonna be my island. All right. Okay. Good. So that's good. And then all of that is recorded. Great.